Joy Varghese from Uncovering Chemistry. Today we are going to discuss about abnormal molar mass. Clear? Now in this, it is from chapter 2 solution topic 2.7 Ncert textbook page 557. This is video 1 what we are going to talk about. Now when we say abnormal molar mass, what we have studied till now, right? We have discussed that colligative property helps us to calculate the molar mass of a solute. So from this we will derive the formula. This is elevation in boiling point what we have discussed. From this we derive the formula from which you can find the molar mass of the solute, right? Now, but when we find molar mass, that is by this formula, sometimes observed or what we call it as experimental value, molar mass are not same as the expected or theoretical molar mass. Means what? Suppose if I find the molar mass of NaOH, so we know the molar mass of NaOH according to our calculation through atomic mass, that is through theoretical base, is 40 U. Clear? What you have studied till now. But if you do find it out by this method, actually this molar mass, that is experimental what we say, or what we call abnormal. What is the word? Abnormal, right? This is normal molar mass what we call, right? So abnormal molar mass of this NaOH will be different, and this difference was explained by whom? So it was explained by Hoff by giving a factor I. Means I'll repeat again, sometimes observed or experimental. Observed means what we say, abnormal or experimental molar mass are not same as expected or theoretical molar mass. So who gave this factor? So it was being given by whom? Hoff. For this, in 1886, Hoff introduced a factor called Hoff factor, which is denoted by small I, to express the extent of association or dissociation of a solute in a solution. So first of all we'll study about what is association and what is dissociation, then we'll study about Hoff factor's definition, right? So when we talk about this part here, always remember, you can see dissociation of solute means if I take a salt of KCl in water, you will see it will get dissociated into K plus and Cl minus ion. Means 1 mole of KCl give 1 mole of K plus ion and 1 mole of Cl minus ion. Means what? In the beginning it was 1 mole, but after dissociation, what is the word? After dissociation it changed into 2 mole. Right? So after dissociation number of moles is increase. Therefore concentration of particle after dissociation also increase, we can say, right? So in this case of dissociation, the Hoff is more than what we call it as factor is more than 1. Means I will be greater than 1. Why? Because beginning it was, when it was undissociated it was 1 mole. After dissociation it become 2 mole, means I value will be greater than 1, to what we say here, right? For electrolytic solution, Hoff factor can be used to calculate the extent of dissociation of degree of dissociation denoted by what? Alpha. Means if you want to find this Hoff factor I value, first of all you need to understand what is degree of dissociation, that is denoted by what? Alpha. So we have taken a nice example here. You can see here for a given reaction, you can see of AB type. AB means 2 ions you can get dissociated. So here if KCl is taken in 100 moles, after dissociation it will be suppose 25 moles. Clear? So suppose here when we say in the initial the concentration will be 1 mole, and here you can say 0 also, I will have written here N also, right? So at equilibrium, if the degree of dissociation is alpha, then here we can call it as N alpha, and the one which is undissociated means we are the one which is left out after equilibrium, we call it as what? 1 minus alpha. Means what is the meaning of what? If 100 moles are there and here 25 moles are there, so what will be undissociated part, that is 25 will be subtracted from 100. So same way here alpha, we can say 1 minus alpha is the undissociated part, what we call, right? Now Hoff factor, when we say, there is a formula. What is the formula? I is equal to total number of particles after dissociation upon total number of particles before dissociation. So before dissociation we have seen how much it was? 1. After dissociation it changed to 2. But according to our this part, equilibrium part, what we have seen, N alpha is after dissociation, and before dissociation it was, sorry, undissociated part is 1 minus alpha. So total number of moles means we will add these two. You can see here what is written here. Total number of moles is equal to 1 minus alpha plus n alpha. So if you correlate this, you will get this formula. So this part I will put it in this formula, that is I is equal to total number of particles. So I plus n minus alpha upon total number of particles before dissociation. So how much it was before dissociation? It was 1, right? So you correlate this. So I will be what? Will be equal to 1 plus n minus alpha. Now if you calculate this further, what you will see? You will derive a formula, that is I is equal to, you just simplify this, you will get I minus 1 means 1 I will take it on the either side. So I minus 1 is equal to n minus alpha. So therefore what is alpha is equal to I minus 1 upon n minus 1. Now this is the formula for degree of dissociation, right? So this you have to remember, right? At the end we will revise this again. Now when we talk about degree of association means what? What happens when acetic acid dissolved in benzene, association of molecule will take place, that is formation of a dimer. Means here this is acetic acid, 2 moles are there. Clear? When it is dissolved in benzene, it combines with each other through a hydrogen bond, what you can see, sorry, here hydrogen bond. So it will become 1 mole, right? And here total in the beginning how many were there? Before association it was 2 moles. After association it became 1 mole. 2 molecules combined. So that's why we call it as combined to form 1 molecule. We call it as a dimer, right? Now after association, number of mole what happened? Decreases. Dissociation what was there? It increased. Here it decreases. Therefore in this case the Van 't Hoff factor will be I will be less than 1. Now for finding degree of association. Now degree of association, you can see example, n simple molecule combined to form an associated molecule, right? So here n is a single molecule combined to form 1 single molecule. You can see here 1 molecule, what we say means 2 molecule combined, 2 molecule combined to form 1 molecule. Now for this we will go through another part of explanation. See here. Now the fraction of solute associated in a solution is called the degree of association. Means what? What is the word given? Associated means combines. Suppose a molecule of A associate to form the associated molecule AN, and its degree of association is what? Alpha. Here also same alpha only will take, how we took for degree of dissociation. Then at equilibrium. So here if you see in this case how this 1 by n came, right? So for this we have one explanation here. You can see here. N moles associate to form 1 mole, right? So if 1 mole, what you call unassociated particles, what we take, then how much will be the associated moles, right? So what is that? Simple cross multiplication, it will become what? 1 by n. A number of moles associate to form 1 moles, n number of moles associate to form 1. So if 1 mole is there, 1 molecule, what we say, then how much will be the association mole? So here simple cross multiplication, it becomes what? 1 by n, what we say, right? Now so this will be clear how this 1 by n came. Now initial concentration is 1 in this case and the final is 0, what we say, right? After association. At equilibrium we can say this is what? Alpha, and this is what? What is this 1 minus alpha means? At equilibrium means unassociated part. Which part? Unassociated part, right? So 1 minus alpha is the unassociated part, this is associated. But why I divided by n? Because we know that ethanoic acid we have discussed, right? 1 plus 1 mole was there, and here it became what? Only 1 mole, means 1 mole combined. This 1 plus 1 means 2 molecules combined to form 1 molecule, what we call it as dimer. What we call it as dimer. See, I will explain. I'll explain that. You can see here. You can see 1 plus 1. How many moles were there? 2. And here they combine to form what? How many moles? Only 1 mole. Means this is 2 and this is 1. So we can say 1. How we got? That is 2 divided by 2 is equal to 1, what we say, right? So if this is alpha, the degree of association alpha, then it will be what? Alpha by 2, what we call, right? Degree of dissociation is what? Alpha, then we can call it as alpha by 2. You understood what I am talking about? Yes or no? So this. Now in this case, so you came to know how this is alpha. So alpha by 2, but here we have taken this general example. So alpha by n. Therefore, total number of particles at equilibrium. So what I will do, I will take this and this both I will add here, right? So therefore, what is Van 't Hoff factor? I is equal to what we have studied. I is equal to total number of molecules upon total number of molecules what? Associated whole upon, what is the word? Total number of molecule associated upon unassociated molecule or mole, whatever we call, right? Unassociated, total number, right? So here the unassociated is 1 here, what you can see here, and this. So what we do, total number of molecules associated means this both I added here, and this, if you correlate this, obviously you can simplify this, and what you will get a formula that is alpha is equal to n into 1 minus n upon n minus. This can also be written as n upon n minus 1 into 1 minus I. Now why this is 1 minus I? Because we have seen in association I is less than 1. So this part you can remember through this part. Okay. Same way you can see the another part. See. Now if you do the revision for association dissociation, you can write down this as a note in your notebook. Polar solute, when dissolved in polar solvent, dissociation will occur, in which molar mass experimental value, that is experimental means what? Abnormal. Right? Abnormal molar mass will be greater than normal molar mass or theoretical value, what we call, right? In this case, degree of dissociation, the formula is alpha is equal to I minus 1. Why? Because dissociation, number of molecules or moles will be greater after dissociation. Therefore, I will be greater than 1. That is I minus 1, what we say. So this is the best way to remember. Whole upon n minus 1 is one formula. Now, when non-polar, what is the word here? Non-polar solute dissolve in a non-polar solvent, then association will occur. Association will occur, and you will see, therefore degree of association alpha is equal to 1 minus I into n upon n minus 1. How we derive that we have discussed in our video. Okay, in this theoretical value will be greater than experimental value. Now here you can remember why I have written 1 minus I, because you can see here what is it? I is less than 1, right? So for dissociation I greater than what? Association I less than 1, and these are the two formulas what you have to remember. Okay, so this is the way these two formulas were derived. Now the next part. So therefore you can see here in association part you can remember this formula also for finding the value of I, right? This is one formula what you remember, 1 minus alpha plus alpha by n divided by 1. Now n is number of moles associated or dissociated, what we call, right? Now this I will explain in the what we call it as numerical part also, how to calculate n in that. Okay, but now the next part is about dissociation. See, okay, now for dissociation when we talk about, you can see here this part what we say here, that is AB dissociated into two ions, what we say. So in that you can see 1 minus alpha, alpha, alpha. So if you calculate this, what will happen for at equilibrium, total number of particles at equilibrium will be what? This can be get cancelled, plus minus, and you will get what? 1 plus alpha. Similarly for AB2 type, AB2 type means what? There are 2 atoms of B and 1 atom of A. So if after dissociation you will see it will be A2 plus and 2B minus. So in this case we will take here what? 2 alpha and here only alpha. So if you add this all, you will get what? This is total number of particles, 1 minus alpha plus 2 alpha, 1 plus 2 alpha. Now for this one nice table is there. This you write it down it as note. See, number of ions are 2, then 1 plus alpha will be total number of particles. Number of ions 3, then 1 plus 2 alpha. Number of ions 4, then 1 plus 3 alpha. So for n number of particles, suppose 5 is there, what you have to keep here? 1 plus 1 minus 5 minus 1 into alpha. So this is the best part what you can remember for finding total number of particle in dissociation, right? So remember this thing, and you can see one another formula you can see here for Van 't Hoff for what you call it as dissociation part, what we say, what is that? 1 plus n minus 1 upon into alpha upon 1, right? Now this is Van 't Hoff factor for dissociation, what I am talking about, right? So this is the formula you can remember, or this alpha what I have already explained in this video, right? So we will stop here. Next time we will continue in the second video of the continuation of what? Van 't Hoff factor. Okay.